चालू की है कि नहीं की थी? अभी की है लेकिन यार
अभी तक स्ट्रीमिंग नहीं लगाया था।
स्ट्रीमिंग लगाया
डोंट
था।
नो, पूछ रहा हूँ।
लग नहीं रहा, मैंने तैयारी सारी करके रखी थी, बस सब लोग आने के बाद मैं स्टार्ट स्ट्रीमिंग पे पुश मारता हूँ, वो शायद नहीं मारा। अभी किया है वैसे। ये कहाँ तक देखा?
नहीं, अभी नहीं था, मतलब बेसिकली स्ट्रीम
स्टार्ट ही नहीं किया हमने।
हाँ, स्ट्रीमिंग नहीं किया,
वन
अच्छा।
वन डे अगो वही दिखा रहा है लास्ट वाला। अभी स्टार्ट हो गया।
ये क्या था? ये वाला वीडियो कहाँ से कितना देखा?
स्टार्ट से ही चालू करो
स्टार्टिंग से करो।
क्योंकि वो हाँ
challenging. Our main goal here is to step through his specific sport. And I think in general, anyone who's played around with one of these models has the clear sense that it's memorized tons and tons of facts. So a reasonable question you could ask is, how exactly does that work? And where do those facts live? Last December, a few researchers from Google DeepMind posted about work on this question, and they were using the specific example of matching athletes to their sports. And although a full mechanistic understanding of how facts are stored remains unsolved, they had some interesting partial results, including the very general high-level conclusion that the facts seem to live inside a specific part of these networks, known fancifully as the multi-layer perceptrons, or MLPs for short. In the last couple of chapters, you and I have been digging into the details behind transformers, the architecture underlying large language models, and also underlying a lot of other modern AI. In the most recent chapter, we were focusing on a piece called attention, and the next step for you and me is to dig into the details of what happens inside these multi-layer perceptrons, which make up the other big portion of the network. The computation here is actually relatively simple, especially when you compare it to attention. It boils down essentially to a pair of matrix multiplications with a simple something in between. However, interpreting what these computations are doing is exceedingly challenging. Our main goal here is to step through the computations and make them memorable, but I'd like to do it in the context of showing a specific example of how one of these blocks could, at least in principle, store a concrete fact. Specifically, it'll be storing the fact that Michael Jordan plays basketball. I should mention the layout here is inspired by a conversation I had with one of those DeepMind researchers, Neil Nanda. For the most part, I will assume that you've either watched the last two chapters or otherwise you have a basic sense for what a transformer is, but refreshers never hurt, so here's the quick reminder of the overall flow. You and I have been studying a model that's trained to take in a piece of text and predict what comes next. That input text is first broken into a bunch of tokens, which means little chunks that are typically words or little pieces of words. And each token is associated with a high-dimensional vector, which is to say, a long list of numbers. This sequence of vectors then repeatedly passes through two kinds of operation. Attention, which allows the vectors to pass information between one another, and then the multi-layer perceptrons, the thing that we're going to dig into today. And also there's a certain normalization step in between. After this sequence of vectors has flowed through many, many different iterations of both of these blocks, by the end, the hope is that each vector has soaked up enough information, both from the context, all of the other words in the input, and also from the general knowledge that was baked into the model weights through training, that it can be used to make a prediction of what token comes next. One of the key ideas that I want you to have in your mind is that all of these vectors live in a very, very high-dimensional space, and when you think about that space, different directions can encode different kinds of meaning. So a very classic example that I like to refer back to is how if you look at the embedding of woman and subtract the embedding of man, and you take that little step and you add it to another masculine noun, something like uncle, you land somewhere very, very close to the corresponding feminine noun. In this sense, this particular direction encodes gender information. And the idea is that many other distinct directions in this super high dimensional space could correspond to other features that the model might want to represent. In a transformer, these vectors don't merely encode the meaning of a single word, though. as they flow through the network, they imbibe a much richer meaning based on all the context around them, and also based on the model's knowledge. Ultimately, each one needs to encode something far, far beyond the meaning of a single word, since it needs to be sufficient to predict what will come next. We've already seen how attention blocks let you incorporate context, but a majority of the model parameters actually live inside the MLP blocks. And one thought for what they might be doing is that they offer extra capacity to store facts. Like I said, the lesson here is going to center on the concrete toy example of how exactly it could store the fact that Michael Jordan plays basketball. Now, this toy example is going to require that you and I make a couple of assumptions about that high-dimensional space. First, we'll suppose that one of the directions represents the idea of a first name Michael, and then another nearly perpendicular direction represents the idea of the last name Jordan, and then yet a third direction will represent the idea of basketball. So specifically what I mean by this is if you look in the network and you pluck out one of the vectors being processed, if its dot product with this first name Michael direction is 1, that's what it would mean for the vector to be encoding the idea of a person with that first name. Otherwise, that dot product would be 0 or negative, meaning the vector doesn't really align with that direction. And for simplicity, let's completely ignore the very reasonable question of what it might mean if that dot product was bigger than 1. Similarly, its dot product with these other directions would tell you whether it represents the last name Jordan or basketball. So let's say a vector is meant to represent the full name, Michael Jordan. Then its dot product with both of these directions would have to be 1. Since the text, Michael Jordan, spans 2 different tokens, this would also mean we have to assume that an earlier attention block has successfully passed information to the second of these 2 vectors, so as to ensure that it can encode both names. With all of those as the assumptions, let's now dive into the meat of the lesson. What happens inside a multi-layer perceptron? You might think of this sequence of vectors flowing into the block, and remember, each vector was originally associated with one of the tokens from the input text. What's going to happen is that each individual vector from that sequence goes through a short series of operations, we'll unpack them in just a moment, and at the end, we'll get another vector with the same dimension. That other vector is going to get added to the original one that flowed in, and that sum is the result flowing out. This sequence of operations is something you apply to every vector in the sequence, associated with every token in the input, and it all happens in parallel. In particular, the vectors don't talk to each other in this step. They're all kind of doing their own thing. And for you and me, that actually makes it a lot simpler, because it means if we understand what happens to just one of the vectors through this block, we effectively understand what happens to all of them. When I say this block is going to encode the fact that Michael Jordan plays basketball, what I mean is that if a vector flows in that encodes first name Michael and last name Jordan, then this sequence of computations will produce something that includes that direction basketball, which is what we'll add on to the vector in that position. The first step of this process looks like multiplying that vector by a very big matrix. No surprises there, this is deep learning. And this matrix, like all of the other ones we've seen, is filled with model parameters that are learned from data, which you might think of as a bunch of knobs and dials that get tweaked and tuned to determine what the model behavior is. Now, one nice way to think about matrix multiplication is to imagine each row of that matrix as being its own vector, and taking a bunch of dot products between those rows and the vector being processed, which I'll label as E for embedding. For example, suppose that very first row happened to equal this first name Michael direction that we're presuming exists. That would mean that the first component in this output, this dot product right here, would be 1 if that vector encodes the first name Michael, and 0 or negative otherwise. Even more fun, take a moment to think about what it would mean if that first row was this first name Michael plus last name Jordan direction. And for simplicity, let me go ahead and write that down as M plus J. Then taking a dot product with this embedding E, things distribute really nicely, so it looks like M.E plus J.E. And notice how that means the ultimate value would be 2 if the vector encodes the full name, Michael Jordan, and otherwise it would be 1 or something smaller than 1. And that's just one row in this matrix. You might think of all of the other rows as in parallel asking some other kinds of questions, probing at some other sorts of features of the vector being processed. Very often this step also involves adding another vector to the output, which is full of model parameters learned from data. This other vector is known as the bias. For our example, I want you to imagine that the value of this bias in that very first component is -1, meaning our final output looks like that relevant dot product, but -1. You might very reasonably ask why I would want you to assume that the model has learned this, and in a moment you'll see why it's very clean and nice if we have a value here which is positive if and only if our vector encodes the full name Michael Jordan, and otherwise it's 0 or negative. The total number of rows in this matrix, which is something like the number of questions being asked, in the case of GPT-3, whose numbers we've been following, is just under 50,000. In fact, it's exactly 4 times the number of dimensions in this embedding space. That's a design choice. You could make it more, you could make it less, but having a clean multiple tends to be friendly for hardware. Since this matrix full of weights maps us into a higher dimensional space, I'm going to give it the shorthand W up. I'll continue labeling the vector we're processing as E, and let's label this bias vector as B up and put that all back down in the diagram. At this point, a problem is that this operation is purely linear, but language is a very non-linear process. If the entry that we're measuring is high for Michael plus Jordan, it would also necessarily be somewhat triggered by Michael plus Phelps, and also Alexis plus Jordan, despite those being unrelated conceptually. What you really want is a simple yes or no for the full name. So the next step is to pass this large intermediate vector through a very simple non-linear function. A common choice is one that takes all of the negative values and maps them to 0, and leaves all of the positive values unchanged. And continuing with the deep learning tradition of overly fancy names, this very simple function is often called the rectified linear unit, or ReLU for short. Here's what the graph looks like. So taking our imagined example where this first entry of the intermediate vector is 1 if and only if the full name is Michael Jordan, and 0 or negative otherwise, after you pass it through the ReLU, you end up with a very clean value where all of the 0 and negative values just get clipped to 0. So this output would be 1 for the full name Michael Jordan and 0 otherwise. In other words, it very directly mimics the behavior of an AND gate. Often, models will use a slightly modified function that's called the JLU, which has the same basic shape, it's just a bit smoother. But for our purposes, it's a little bit cleaner if we only think about the ReLU. Also, when you hear people refer to the neurons of a transformer, they're talking about these values right here. Whenever you see that common neural network picture with a layer of dots and a bunch of lines connecting to the previous layer, which we had earlier in this series, that's typically meant to convey this combination of a linear step, a matrix multiplication, followed by some simple term-wise non-linear function like a ReLU. You would say that this neuron is active whenever this value is positive, and that it's inactive if that value is 0. The next step looks very similar to the first one. You multiply by a very large matrix and you add on a certain bias term. In this case, the number of dimensions in the output is back down to the size of that embedding space, so I'm going to go ahead and call this the down projection matrix. And this time, instead of thinking of things row by row, it's actually nicer to think of it column by column. You see, another way that you can hold matrix multiplication in your head is to imagine taking each column of the matrix and multiplying it by the corresponding term in the vector that it's processing, and adding together all of those rescaled columns. The reason it's nicer to think about this way is because here the columns have the same dimension as the embedding space, so we can think of them as directions in that space. For instance, we will imagine that the model has learned to make that first column into this basketball direction that we suppose exists. What that would mean is that when the relevant neuron in that first position is active, we'll be adding this column to the final result. But if that neuron was inactive, if that number was 0, then this would have no effect. And it doesn't just have to be basketball. The model could also bake into this column many other features that it wants to associate with something that has the full name Michael Jordan. And at the same time, all of the other columns in this matrix are telling you what will be added to the final result if the corresponding neuron is active. And if you have a bias in this case, it's something that you're just adding every single time, regardless of the neuron values. You might wonder what's that doing? As with all parameter-filled objects here, it's kind of hard to say exactly. Maybe there's some bookkeeping that the network needs to do, but you can feel free to ignore it for now. Making our notation a little more compact again, I'll call this big matrix W down, and similarly call that bias vector B down, and put that back into our diagram. Like I previewed earlier, what you do with this final result is add it to the vector that flowed into the block at that position, and that gets you this final result. So for example, if the vector flowing in encoded both first name Michael and last name Jordan, then because this sequence of operations will trigger that AND gate, it will add on the basketball direction, so what pops out will encode all of those together. And remember, this is a process happening to every one of those vectors in parallel. In particular, taking the GPT-3 numbers, it means that this block doesn't just have 50,000 neurons in it, it has 50,000 times the number of tokens in the input. So that is the entire operation. 2 matrix products, each with a bias added, and a simple clipping function in between. Any of you who watched the earlier videos of the series will recognize this structure as the most basic kind of neural network that we studied there. In that example, it was trained to recognize handwritten digits. Over here, in the context of a transformer for a large language model, this is one piece in a larger architecture, and any attempt to interpret what exactly it's doing is heavily intertwined with the idea of encoding information into vectors of a high-dimensional embedding space. That is the core lesson, but I do want to step back and reflect on 2 different things. The first of which is a kind of bookkeeping, and the second of which involves a very thought-provoking fact about higher dimensions that I actually didn't know until I dug into transformers. In the last 2 chapters, you and I started counting up the total number of parameters in GPT-3 and seeing exactly where they live, so let's quickly finish up the game here. I already mentioned how this up projection matrix has just under 50,000 rows, and that each row matches the size of the embedding space, which for GPT-3 is 12,288. Multiplying those together, it gives us 604 million parameters just for that matrix. And the down projection has the same number of parameters, just with a transposed shape. So together, they give about 1.2 billion parameters. The bias vector also accounts for a couple more parameters, but it's a trivial proportion of the total, so I'm not even going to show it. In GPT-3, this sequence of embedding vectors flows through not 1, but 96 distinct MLPs, so the total number of parameters devoted to all of these blocks adds up to about 116 billion. This is around 2/3 of the total parameters in the network, and when you add it to everything that we had before for the attention blocks, the embedding, and the unembedding, you do indeed get that grand total of 175 billion as advertised. It's probably worth mentioning there's another set of parameters associated with those normalization steps that this explanation has skipped over, but like the bias vector, they account for a very trivial proportion of the total. As to that second point of reflection, you might be wondering if this central toy example we've been spending so much time on reflects how facts are actually stored in real large language models. It is true that the rows of that first matrix can be thought of as directions in this embedding space, and that means the activation of each neuron tells you how much a given vector aligns with some specific direction. It's also true that the columns of that second matrix tell you what will be added to the result if that neuron is active. Both of those are just mathematical facts. However, the evidence does suggest that individual neurons very rarely represent a single clean feature like Michael Jordan. And there may actually be a very good reason this is the case, related to an idea floating around interpretability researchers these days known as superposition. This is a hypothesis that might help to explain both why the models are especially hard to interpret and also why they scale surprisingly well. The basic idea is that if you have an n-dimensional space and you want to represent a bunch of different features using directions that are all perpendicular to one another in that space, that way if you add a component in one direction, it doesn't influence any of the other directions, then the maximum number of vectors you can fit is only n, the number of dimensions. To a mathematician, actually, this is the definition of dimension. But where it gets interesting is if you relax that constraint a little bit and you tolerate some noise. Say you allow those features to be represented by vectors that aren't exactly perpendicular, they're just nearly perpendicular, maybe between 89 and 91 degrees apart. If we were in 2 or 3 dimensions, this makes no difference. That gives you hardly any extra wiggle room to fit more vectors in, which makes it all the more counterintuitive that for higher dimensions, the answer changes dramatically. I can give you a really quick and dirty illustration of this using some scrappy Python. that's going to create a list of 100 dimensional vectors, each one initialized randomly, and this list is going to contain 10,000 distinct vectors, so 100 times as many vectors as there are dimensions. This plot right here shows the distribution of angles between pairs of these vectors. So because they started at random, those angles could be anything from 0 to 180 degrees. But you'll notice that already, even just for random vectors, there's this heavy bias for things to be closer to 90 degrees. Then what I'm going to do is run a certain optimization process that iteratively nudges all of these vectors so that they try to become more perpendicular to one another. After repeating this many different times, here's what the distribution of angles looks like. We have to actually zoom in on it here, because all of the possible angles between pairs of vectors sit inside this narrow range between 89 and 91 degrees. In general, a consequence of something known as the Johnson-Lindenstrauss lemma is that the number of vectors you can cram into a space that are nearly perpendicular like this grows exponentially with the number of dimensions. This is very significant for large language models, which might benefit from associating independent ideas with nearly perpendicular directions. It means that it's possible for it to store many, many more ideas than there are dimensions in the space that it's allotted. This might partially explain why model performance seems to scale so well with size. A space that has 10 times as many dimensions can store way, way more than 10 times as many independent ideas. And this is relevant not just to that embedding space where the vectors flowing through the model live, but also to that vector full of neurons in the middle of that multi-layer perceptron that we just studied. That is to say, at the sizes of GPT-3, it might not just be probing at 50,000 features, but if it instead leveraged this enormous added capacity by using nearly perpendicular directions of the space, it could be probing at many, many more features of the vector being processed. But if it was doing that, what it means is that individual features aren't going to be visible as a single neuron lighting up. It would have to look like some specific combination of neurons instead, a superposition. For any of you curious to learn more, a key relevant search term here is sparse autoencoder, which is a tool that some of the interpretability people use to try to extract what the true features are, even if they're very superimposed on all these neurons. I'll link to a couple really great Anthropic posts all about this. At this point, we haven't touched every detail of a transformer, but you and I have hit the most important points. The main thing that I want to cover in a next chapter is the training process. On the one hand, the short answer for how training works is that it's all backpropagation, and we covered backpropagation in a separate context with earlier chapters in the series. But there is more to discuss, like the specific cost function used for language models, the idea of fine-tuning using reinforcement learning with human feedback, and the notion of scaling laws. Quick note for the active followers among you, there are a number of non-machine learning related videos that I'm excited to sink my teeth into before I make that next chapter, so it might be a while, but I do promise it'll come in due time.
यो तेरा समरी एक बार और भी दे सकता है अपन, क्योंकि मतलब फुल, नॉट जस्ट लीनियर लेयर वाला, बट ऑल्सो प्रीवियस वाला एक बार, ऐसे भी सॉलिडिफाई होगा अपना अंडरस्टैंडिंग और लाइव स्ट्रीम में भी आएगा.
एम्बेडिंग से आगे अटेंशन.
हाँ, एम्बेडिंग अटेंशन और ये अभी वाला लीनियर लेयर भी.
Yeah, I think what we had seen till the last video was the fact that we'll have an embedding layer. Do we call it a layer? What do we call it? Embedding layer.
Following each initial
and an unembedding layer at the end. So whatever text you're passing through the model, the first step in the model is embedding that text into a roughly 12,000 dimensional vector space, which gives, broadly speaking, every word one embedded vector. And it passes through several stages, and finally whatever vector you get, you unembed it so that you eventually spit out the next word in the sequence, like next word to be predicted in the sequence. Um, what happens in the middle is you have an attention layer and an MLP. So in terms of the attention layer, you have what is known as an attention head, which is a combination of three things: a query matrix, a key matrix, and a value matrix. So once you have the embedded vector with you, you pass that through query matrix and key matrix, and essentially take a dot product of the query and key matrices, and then you run a softmax through on each column to kind of normalize the values. Please feel free to add stuff in between, like I might be missing stuff. So you get what is known as an attention pattern. So for example, if you have something like fluffy blue creature, then the word creature is actually referring to something or related to something which is fluffy and blue. So the embedding of creature should eventually change to something which adds this fluffy and blue characteristic to it. And for that, you're multiplying it with the key and query matrices to give you this fresh attention pattern at the end of this operation. Then this attention pattern, basically for it to sum up to 1 in every column here, like the column for creature, you apply softmax so that it adds up to 1. But also before applying softmax, you have all the bottom triangles, so to speak, set to 0. If you can show it with the cursor.
You said to negative infinity, so that softmax changes.
Yeah, yeah. So that softmax changes it to 0. And
that is
then
that is specific to GPT wala case, because you don't want following tokens to influence preceding tokens, because you're trying to parallelly train on the same line a fluffy blue creature roam the verdant forest. It's not just one input. It is another input. A fluffy is another input. A fluffy blue is another input. And if you were to have later tokens influence second, then that training might not happen in parallel. So you don't want the later tokens to influence ye pehle wale. So that's why you. But again, like I said, there are some cases where that may not be like the translation example he gave. That may not be relevant, and in that case, you wouldn't do negative infinity on the bottom layer. So
yeah, so this is a self attention head. But in a cross attention head, you don't do that. That's different. Then this whole thing is multiplied by the value matrix, which is made up of a value up and value down matrix for simplicity purpose. And eventually you get like this completes the attention head. So you have the query matrix, the key matrix, and the value matrix, which itself is value up and value down. So multiply each embedding by value vector, and then you add it to the original embedding. That's what you do basically. What you get out of this, you add it back to the original embedding. So you're updating the embedding to kind of include the attention metrics to it in a way. And then this final matrix that you get, you pass it through an MLP, which is roughly or usually equal to 4x, or in GPT-3, it's equal to 4 times the attention space. And this MLP itself has an up projection and a down projection. And in GPT-3, it is there are 96 such MLPs. And finally, what you get, you unembed it, and eventually you get the final word out of it. And one point that he mentioned just recently in this last video was the fact that you want your like you if you have an n dimensional space, then you can typically encode only n vectors in it, because you want each vector to be like perpendicular to the other vector. But if you allow for just plus minus 1 degree in each dimension, then the number of vectors that you can encode goes up exponentially. And this is why for an n dimensional space, you can have many more kind of concepts encoded into it. Sorry?
Yeah, features. Yeah, correct.
Features, yeah. And I think we spoke also about in the MLP how it is kind of learning facts in the MLP layer, and basically the embeddings of different words are combined. Like Michael Jordan plays basketball. If you want to predict that he plays basketball, then the word for Michael is like the embedding for Michael is combined with the embedding for first name to give you a direction that, okay, this Michael refers to first name, then Jordan to second name, and then both together are combined to form a full name, which is Michael Jordan. And then the weights of the MLP have been trained already to kind of say that Michael Jordan and basketball all come together. So when this embedding comes in of Michael Jordan first name, second name, or rather full name, then the product of it with the neuron, I mean, although technically it's not a single neuron, which encodes this, which it ends up giving a high number for basketball. So I think that's how, while it's not very clear, that's how it suggests that facts are being learned by the MLP. And from what I have kind of heard some others speak about it, like you can sometimes make a light network. So a large part of the network parameters are actually residing in this MLP layer. And if you make the MLP layer very sparse, then of course the model parameters, the size of the model becomes very small compared to a typically large MLP layer. But that also means that it doesn't learn facts. So you could typically have a smaller model which doesn't know facts, but at least it's good at the attention part, and it's good at semantic relationships. So that's how you make smaller models which don't really know any facts, but they are still good at understanding, so to speak, English. So that's something we'll probably get to in the later stages of learning this. But uh, basically the a large percentage of the weights reside in the MLP layers of the this entire transformer that we are talking about.
Right. I just wanted to talk a little bit about this query and key again.
Yeah.
Query and key matrix. These are lower dimensional. मतलब one was
Yes.
this 12,000 embedded dimensions वाला value matrix भी
Mm-hmm.
था and then embedded vectors भी उसमें था. But query and key matrix are a much lesser dimension. The vectors that get produced 128, and I think the way I see it is query and key essentially, so all you want to do is your e1 e2 e3 e4 embedded representation of each of this token coming in into a single attention block. At the end what you want is an updated nuanced or learned or imbibed context rich meaning. So
Mm-hmm.
essentially you want e1 dash e2 dash to come out of it, and of course this is happening at multiple blocks. So you basically it's sort of an not an average but an addition of combining all that in pipe. But query and key in itself is basically sort of a like this wq and wk that gets learned in the process is essentially asking questions within this sentence, right, or within this input, as to which part of which other part of this input could basically influence me, is what query is
Mm-hmm.
asking, and key is saying okay, I could be the one that could potentially be influencing you. And this all is happening at the lower dimension because this is just because the number of relationship that might exist between two tokens could be much smaller than what a word might have to include as part of when it imbibes everything in itself. So query मतलब ये हो सकता है कि the example that he gave was a specific one where he's saying creature is sort of an asking, if I'm a noun, what are the adjectives that are preceding me that might influence me? So that is one type of a query. Of course, there are, and even in one query might contain maybe different features, different questions. And likewise, there are multiple multi heads and multi layers. So you can imagine a lot of this different things getting asked to find out relationship between. But the point I was for for antiquity, what I'm saying is कि ये जो query and key है, those are matrices, those are vectors in lower dimensions that are only trying to identify in this input which token might be related to which other token. And then once you determine
Yeah.
that, which is shown in bigger blobs here, then you actually, when you know कि this query, this position gets influenced by this, तो उसका जो value matrix है, that is again in the higher dimension, and that you can very well see because E3 को अगर E dash 3 करना है और E3 खुद 12,000 का है, तो वैल्यू को भी 12,000 वाला होना पड़ेगा. बट वैल्यू जो 12,000 वाला था वो उसी को इम्पैक्ट करेगा जिसके लिए सर्कल बड़ा था, जिसका ये की और क्वेरी ने काम करके चुका होगा. तो ये सॉर्ट ऑफ वेटेड सम देगा उसके लिए कि किस वैल्यू को ज़्यादा तवज्जो देना है. और या दैट वाज द पॉइंट आई वाज. और आई वाज आल्सो वंडरिंग कि क्वेरी और की का थोड़ा सा साइज बढ़ा लिया तो उसका क्या मतलब होगा. से 256 किया, डबल किया तो समथिंग रिलेटेड टू, नॉट इमीडिएटली मे बी, छोटी छोटी चीज़ें करने के बाद, मेन चीज़ें करने के बाद, ये बाद में. शर्मा जी.
No, that's fine. I think it properly summarized.
हम्म,
Only thing at last what they mentioned about is like the relationship that they are talking about the vectors, right? In linear stuff, they are mentioning that it may leads to like multiple neurons will be accommodating the single answer. That's what later we identify. That's the only thing.
right. Yeah, I think that is what like Arjun was saying. I think one thing he's trying to say कि दुनिया में इतने सारे फैक्ट्स है, इतने सारे क्वेश्चन है, इतनी वैरायटी है, वो इतने से 4 इंटू वट एवर 12,000 50,000 में फीचर में कैसे आ सकते हैं इतने से डायमेंशन में। तो उनका कहना है कि इतने से डायमेंशन भले ही हो, अगर द वेक्टर्स दैट यू आर प्रोड्यूसिंग, और पाइथन का एग्जांपल उसने जो बना के दिखाया, तो थोड़े से लीवे उसको मिलने पे वो बहुत सारे फीचर्स एनकोड कर सकता है। आई डोंट नो इफ ही सेड कि ही नोस इट फॉर श्योर और दैट जस्ट अ स्पेकुलेशन।
The speculation will be based on the context every time. No, because same neurons for different context will be saying the different answer. That's it.
राइट। कल अपन ये कर सकते हैं कि गेट अ सेंस ऑफ दिस थिंग, तो वो कारपति वाला ये देख सकते हैं बिफोर वी कैन, क्योंकि ये मॉडल ऐसा नहीं है कि CNN नारायणन की तरह कैगल पे करके देख लिया, राइट। इनफैक्ट कारपति वो करता भी है, वो छोटा नैनो जीपीटी बनाएगा। इनफैक्ट वही करते हैं अपन। इसके पहले कि वी स्टार्ट मूविंग इनटू लाइक व्हाट द दुनिया इज़ डूइंग दिस डेज, एजेंटिक और ये वो सब करने से पहले थोड़ा इसका इनटू द बोन्स अंडरस्टैंडिंग लेना है। तो एक बार आई थिंक, और उसने भी वैसे भी बताया ही था कि कारपति वाला वीडियो का उसका भी रेफरेंस था ही। ट्राई टू फाइंड आउट, यू कैन ऑल्सो फाइंड आउट इफ देयर इज एनी अदर बेटर रेफरेंस जिसमें थोड़ा हैंड्स ऑन करके देख सकते हैं। ये यूट्यूब पे रिलैक्स करके वीडियो और फिर चर्चा एक जगह है, बट आई थिंक करने पे थोड़ा और एक बेहतर फीलिंग आएगा। एंड इसके रिसोर्सेज, करने वाले रिसोर्सेज उतने नहीं होंगे जितने बाकी डीप लर्निंग के सब्जेक्ट्स पे है। सो ऐसी कोई क्यूरेटेड लिस्ट है, ऐसा कुछ मिला अच्छा तो देन वी कैन टेक दैट। बाकी एक मुझे जितना मुझे पता है वो कारपति वाला एक तो है ही। ऑल राइट।